Section 25 of the Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Chelsea Woods. The Science, History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy, Chapter 17, Saturn. The planet Saturn was considered by the ancient to be the most distant of the moving heavenly bodies, a position it retained even after the triumph of the Copernican ideas and the establishment of the modern conception of the solar system. The reason for this was that the period of its oscillatory motion to and fro in the heavens was the longest of all the planets. The ancients noted that it took 29.5 years for Saturn to return to the same place among the stars, as compared with 12 years for Jupiter, and correspondingly less for the other planets, down to 88 days for Mercury. Accordingly, they considered Saturn was the most distant. Eudoxus, approximately 409 BC to approximately 356 BC, as has been shown, believed that the motion of Saturn, as in the case of Mars and Jupiter, could be represented roughly by supposing that each planet oscillated to and fro on each side of a fictitious planet which moved uniformly around the celestial sphere in or near the ecliptic. The slow period of Saturn also made it the most distant of the planets in the system as devised by Copernicus, who computed its distance from the Sun as 9 times that of the Earth, which may be compared to his credit with the modern figure of 9.5 times. After the development of observational astronomy, Tycho Brahe in 1563 made his first recorded observation at the University of Leipzig, noting the close approach of Jupiter and Saturn, which he found was quite a month in error in the prediction of the Alfonsine tables, published in Spain in 1252 and in general use by astronomers throughout Europe. The next important observation of Saturn was indeed of epoch-making significance in astronomy. With this new telescope, it was but natural that Galileo should examine Saturn as he did the other planets. Turning his telescope towards Saturn, he observed that planet too was not single and complete, but apparently consisted of 3 parts, or, as it appeared in the drawing made by him at the time, of a central body and 2 satellites in close proximity, which naturally seemed to resemble those of Jupiter. At subsequent observations he failed to see more than the central and larger portion, and consequently, completely baffled, he left the problem as a legacy to his successors. The 2 appendages were seen and described under varying conditions by a number of astronomers, but the true solution was first furnished by Huygens, 1629 through 1695. When he studied with one of his powerful telescopes the appearance of the planet. Huygens announced in 1655 that he had discovered a single satellite, which he named Titan. With a still more powerful instrument, he found that the effect of 2 component bodies observed by Galileo was due to the fine ring which surrounded the planet and was inclined at a considerable angle to the plane of the ecliptic and consequently to the plane in which Saturn proceeds around the Sun. As the ring was extremely fine, it became invisible, either when its area was directly opposite to the observer or when it was directed toward the Sun. As in that case, it received no light for reflection. Near this opposition, or invisibility, the ring appears to be foreshortened, and presents the appearance of 2 arms projecting from the body of the planet. The ring, of course, gradually widens from its opposition or invisibility, and the opening becomes visible, a period of 7 years elapsing between such a state and when the ring is seen at its widest. With the observation of Huygens, the reason for Galileo's varied observations were furnished. To make this matter more conclusive, Huygens collected and published a series of early drawings by various observers, which drawings he compared with his own observations. Thus, what Galileo conceived as 2 satellites was really the ring when seen with its greatest breadth. The disappearance of these satellites occurred when the edges of the ring were presented to his view, the revolution of the planet giving an observer on Earth a series of phases in which the appearance of the planet is remarkably different. What Huygens saw is now familiar to everyone who has observed Saturn through a telescope. Surrounding the central body are rings parallel to the planet's equator, but inclined about 27 degrees to the plane of its orbit and 28 degrees to the ecliptic. Their nodes begin at longitude 168 degrees in Aquarius and at longitude 348 degrees in Leo. The plane of the rings remains sensibly parallel to itself for a very long time. For 15 years, or half a revolution of Saturn, their northern face is seen, and during the remaining half of the revolution, their southern face. When the Earth passes over the plane of the rings at a time of transition, their edge is presented so that the ring virtually disappears from view, as occurred, for example, in 1908, and in 1612 had occasioned Galileo's perplexity. The thickness of the rings is less than 100 miles. Consequently, their edge was quite invisible through his feeble telescope. The disappearance of the rings reoccurs at intervals of about 15 years. In 1675, Giovanni Domenico Cassini, 1625 through 1712, noticed a dark marking in the ring which later was found to mark the division of the ring into two distinct schemes, a narrow and an outer ring, to which the name of Cassini's division was given. As was natural, the peculiar construction of the rings of this planet and the accompanying satellites was the subject of deep and earnest inquiry, both mathematical and telescopic, though but little substantial progress was made in explaining the formation and occurrence. In his analysis of the nature and motions of the planets and their satellites, the mechanical problem of the stability of Saturn's rings was left even by Laplace in a very unsatisfactory condition, for he made no attempt to determine the kind or amount of irregularity in the distribution of their weight, which he assumed was necessary in any considerations of them as rotating solid bodies. In 1849, W.C. Bond at Cambridge, Mass., found that Saturn was accompanied by a third comparatively dark ring, lying immediately within the bright rings, and to this the name crepe ring has been applied. Professor Bond, who devoted much attention to the study of Saturn, at first denied the solidity of the planet's structure and asserted that the fluctuations in its aspect were entirely at variance with any such hypothesis. He and other astronomers had frequently detected in both of the bright rings fine dark lines of division, and as these frequently lapsed into imperceptibility, the condition was due, in his opinion, to the real mobility of their particles, and indicated a fluid formation. The known solidity of the rings was then demonstrated on abstract grounds by Professor Benjamin Pierce of Harvard University, who maintained that they were formed by streams of some fluid denser than water. In 1857 in England, James Clerk Maxwell, the famous mathematician and physicist, presented a mathematical discussion on the subject, in which he stated that neither solid nor fluid rings could exist and that the system could be composed only of a great multitude of uncollected particles which revolved independently in a period corresponding with their distance from the planet. This idea of a satellite formation, remarkably enough, had been several times entertained and lost sight of, so that when advanced by Maxwell it was a virtual novelty. The hypothesis met the test of telescopic observation. The mathematical theory of the ring system found an analogy in the assemblage of planetoids, both visible and invisible, which are known to be revolving around the Sun, with orbits situated between Mars and Jupiter. If seen from a considerable distance, such a swarm of these small particles would give the impression of a continuous solid body, so that on its physical basis this theory did not seem improbable. It was pointed out by Kirkwood in 1867 that the division between the two main orbits, first made by Cassini, could be explained by the perturbations due to certain of the satellites, just as the corresponding gaps of the minor planets are explained by the action of Jupiter. But in modern astronomy, the probability of a mathematical theory is not sufficient, and its acceptance must depend on direct and conclusive evidence from telescope, spectroscope, or photographic plate. This was supplied most effectively by Professor James E. Keeler, 1857 to 1900, at Allegheny Observatory, Pittsburgh, in 1895. He pointed his spectroscope to the planet and found by examining the light waves from opposite sides that the main body was in rotation. The light from one side was approaching the Earth, and from the other it was receding. This rotation of the planet, of course, had been realized for some years, but the axial rotation of the rings had never before been demonstrated, and this Keeler provided, revealing the strange fact that the interior part of the rings rotated faster than the exterior, which of course would not hold true in the case of a solid body. The motion slowed off outward in agreement with the diminishing speed of particles traveling freely, each with its own orbit. The visibility of the rings when the Sun and the Earth are on opposite sides of their plane is explained by Professor Barnard as due to the filtration of sunlight through a cloud of cosmical dust. He regards the knots as the result of the radiation of parts of the clouds, which are denser, but not necessarily thicker than the rest under the illumination of sunlight, which gives to them their adjacent portions of less density. Percival Lowell, however, believes that the rings of Saturn are not flat and of uniform thickness, but rather resemble a concentric series of tores or anchor rings, and that the knots represent their fixed portions. Professor Sir G.H. Darwin explains the rings of Saturn by considering them an abortive satellite, scattered by tidal action into annular form, for they lie closer to the planet than is consistent with the integrity of a revolving body of reciprocal bulk. This interesting appendage, according to Professor Darwin, will eventually disappear, as the constituent particles will be dispersed inward in part and will be gathered to the surface of the planet, while in part they will scatter outward where they may coalesce unhindered by the strain of unequal attraction. Then one modest planet revolving within Mimas would be all that would remain of appurtenances which lend character to the planet. The dimensions of these wonderful rings of Saturn doubtless will arouse the reader's curiosity. The plane itself has an equatorial diameter of 75,000 miles. Outside of this first comes the crepe ring at a distance from 9 to 10,000 miles of clear space, and somewhat less than 10,000 miles in width. The crepe ring is joined to the second ring, which is the most brilliant and is about 16,500 miles in width. Then comes a gap of about 16,000 miles, and there lies the outer ring, 10,000 miles in width, with an exterior diameter of about 168,000 miles. Hence, the entire ring system has a width between 36,000 and 37,000 miles. A model of the outer ring constructed on the scale of 10,000 miles to the inch could be made with an approximation to accuracy from a sheet of writing paper nearly 17 inches in diameter. Cassini's discovery of the dark markings in Saturn's ring was one result of a series of telescopic observations which he made of the planet, in which he discovered 4 new satellites: Iapetus in 1671, Rhea in 1672, and Dione and Thetis in 1684. This list of satellites was increased by 2 more in 1789, when Herschel, using his 40-foot telescope for the first time, August 28, detected a 6th satellite of Saturn, Enceladus, and on September 17th discovered a fainter satellite, Mimas. Both of these were nearer to the planet than any of the 5 previously observed. In September 1848, W.C. Bond of Cambridge, Mass., discovered Hyperion, and 2 days later this same satellite was also observed at Liverpool by William Lassell. A 9th satellite of Saturn, Phoebe, was discovered by Professor W.H. Pickering on photographic plates taken at the Harvard University Observatory at Arequipa, Peru, and was announced in July 1904, the satellite being seen on a number of recent photographs. This satellite is much smaller than any of the existing moons, so much so, in fact, that it is beyond the visibility of the human eye with any existing telescope. It revolves around Saturn at a distance of many millions of miles, far beyond the orbit of Iapetus and with a period correspondingly longer, and strange to say, in an opposite direction from its fellows. Professor Pickering also discovered in 1905 a 10th satellite of Saturn, Themis, which revolves much closer to the planet. It is said to be the faintest object in the solar system, and it is a striking illustration of what astronomical photography can accomplish in a way of discovery. Saturn moves in an orbit which is somewhat more eccentric than that of Jupiter, but which is at a mean distance from the Sun of 886 million miles. The equatorial diameter is about 75,000 miles, and the polar diameter is about 68,000, giving it a mean diameter of 73,000 miles, or a little more than 9 times that of the Earth, and a volume greater by 760 times. Yet Saturn is a very light body, having a mass only 95 times that of the Earth and a density of 1/8, which would give it a specific gravity of 5/7 that of our own planet. The same arguments advanced in favor of a high temperature for Jupiter can be issued with increased force in the case of Saturn. It may be assumed that a large portion of this bulky globe is composed of heated vapors which are vigorously circulated by the process of cooling. Professor Asaph Hall of Washington in 1876 made observations of the white spot, which was visible on the surface of the planet for some weeks. He established a period of rotation of 10 hours, 14 minutes, and 24 seconds, which agrees closely with 10 hours, 16 minutes determined by Herschel in 1794. Hall's value has been confirmed by other observers and is generally accepted. Saturn shows belts similar to those of Jupiter, with a brilliant zone at the equator. The edges of the disk are not so brilliant as the center portion, for the pole of the planet is at times marked with a darkish cup of greenish color. End of section 25.